So let's do a problem that involves first order decay. So they tell you that this reaction decays via first order kinetics. So if it's going to decay by first order kinetics, pH3 will decay by first order. Then you're going to use the equations associated with first order decay. And this is the profile for something of a reactant that's going to go down by first order kinetics. And not something you need to memorize. This is a cheat sheet that I give out to students. And you can use your own or find another internet source. But the decay, remember the key word here is decay. The decay is going to go by these equations. Also the half-life for something that's first order, it goes by this equation. Remember, the half-life is the time. It's actually a time required for a substance to decay to 50% of its original value. So these are the equations we will use. Let's go ahead and read this problem here. So given this equation, they tell you that this pH3 is going to decay at 680 degrees C. It's going to decay with a half-life of 35 seconds. That means after 35 seconds, 50% of this is gone. Calculate the first order rate constant for the reaction. Again, this is what you want to consult, whatever version that is made available to you. And they tell you here, half-life is going to be the natural log of 2 over k. So automatically we have a way to solve for part A. So let's go ahead and solve part A really quickly. Now this is for first order decay, right? So the half-life they tell us is 35 seconds. I'm just going with what's in the problem. The 0.693 natural log of 2 is part of the formula. And all we have to do now is just solve for k. So k is going to equal to 0.693 divided by 35 seconds. Okay, so while half-life is a time, seconds, minutes, hours, where 50% of it decays, the rate constant is not a time. Okay, the units here, when we do the math, is inverse seconds, or seconds to the power of -1. And doing this on my calculator, I'm getting a value of about 0.0198 seconds to the -1. Okay, or how comfortable you are with exponents, you can just go ahead and leave it as is. Okay, both are right answers and represent the answer to part A. For a time required for 95% of the pH3 phosphine to decay. Okay, so 99% of the pH3 phosphine to decay. First of all, we need to utilize our right equation. So the equation we're going to use is this one. You can use that one, but I'm going to use the one with the natural logs. So it's the natural log of A equals to the initial. So that little not subscript there represents initial minus rate constant K, which we solved for, times T. All right, so A is at some time T. A is initial. So initially, let's just say we're at 1. So we'll say our initial is 1. And then at some time t, that time is what we're trying to solve for, we want 95% of it to decompose. Going back to this problem, the time required for 95% of it to decompose. Well, after 95% of it decomposes, you're left with 0.05. Okay, the concentration, whatever those concentration units are. They don't really tell us the concentration, they just say 100, let's just say 95% decayed, that's what the problem tells us. So I'm going to use initially you're at 100%, I'm just calling it 1. And then after time t, you're at 0.05, after 95% of it decomposes. So natural log of 1, which is actually 0 for a sub naught, minus k, which we solved in our previous problem as 0.0198 inverse seconds. 0.0198 inverse seconds. And t is what we're trying to solve for. That equals to the concentration after that time t, where 95% of it decomposes. When 95% of it decomposes, you are left with 0.05. All right, so this, following the same model, we're putting in numbers here. So natural log of 1 is actually 0. So we're at natural log of 0.05, which is something you'll have to get from your calculator, equals to minus 0.0198 seconds at the denominator times t. So we're going to take that minus 0.0198 and divide it. So it's going to be natural log of 0.05 divided by, so minus a 0.0198. So inverse seconds, so the seconds is on the denominator, but it gets flipped. Remember, if you have a fraction in the denominator, the units in the denominator get flipped up to the numerator. So the seconds actually move up, and that is going to be our time t in seconds. So doing this on my calculator, I'm getting an answer of about 151.3 seconds. So at 151.3 seconds, this molecule, if it's going to decay by first order kinetics, this molecule pH3 at 151.3 seconds, 95% of this phosphine will have decomposed at this temperature. Remember, rate constants are very specifically quoted at a specific temperature.